Okay, this lesson's called Linearization and Differentials. And in fact, we're going to leave the differentials out and see if we have time at the end of the course to bring that in, because of all the optional topics in here. It's a great topic, but it's very optional. And so if we don't get to that, that's no big crime, but we'll leave that to the end. So linearization is the big thing here. Let me just get out my pen there and say, okay, well, we're not even really going to talk about differentials today. So let's talk about local linearity. And it says a little review here, but I'm not sure how much of a review it is. But we just have to bring something up that was maybe only partially obvious before. Recall that when we refer to the slope of a curve, we're actually referring to the slope of a tangent line. See, curves don't precisely have slopes. We have to say, okay, we're going to draw a tangent line there to find out what the rate of change is there. So, but the thing is, if we stay close enough to the point of tangent line, the tangent line actually is a good representation of the curve. So the tangent line we use to represent the curve, and if we're very close to the point that we're talking about, then it's a good representation. So for this reason, we say differentiable curves are locally linear. Recall the following illustration of local linearity from an earlier lesson. So you got this crazy curve, and if we zoom in at x equals 2, and zoom in, and zoom in, and zoom in, eventually we see that it's actually pretty flat. Now, that's because it's on a flat screen like that. I mean, in a video lesson like this, we have a better opportunity to do that zooming. I'm just going to switch over to Desmos here, and I'm going to graph a function. I'll just put in some values here and come up with a function that would have a nice curve to it. So I'm going to go y equals x to the power of 4. And then I want an x cubed term, so I'm going to go plus x power 3. And then I want an x squared term, so I'm going to go like minus 5x squared, just to give this thing a little bit of life. And then maybe like a plus 1, so everything's in there. And I want you to check this out. I'm going to really zoom in on one particular point, and that's this minimum here. That I hope you agree, this minimum right there that I've zoomed in partially here looks very curvy. Yeah, it's got a lot of curve to it. You wouldn't say that it has local linearity zoomed in that part. But if I just zoom and zoom and zoom, and if I keep zooming, I hope you're seeing what happens here. Eventually, well, it looks pretty linear. So we say it has local linearity. And local is such a powerful word because when we say local, we just mean close enough. Close enough. You say, well, how close? I'm like, well, close enough. I don't know. It depends on what you're working on. It depends on how much accuracy you want. But if you zoom in enough, it's going to look linear. And you face this every day of your life. We act like the earth is flat. When you walk around on the earth, we rock around and treat it like it's flat. But it's not flat. It's very curved. It's very curved. However, if we're close enough, we stay in a small location, we just treat it as flat. And that's a perfectly good estimate. When you throw a baseball through the air, you don't bring into you don't bring into your thoughts, oh, and then it's going to curve away from me. But if you fire a ballistic missile, then you have to take into account the curvature of the earth. And if you're flying a paper airplane across your living room, you don't take into account the curvature of the earth. But if you're on an airplane flying from North America to Europe, why, you got to take into account the curvature, because over that distance, the earth is not flat. It's curved like this, okay? So when we say local linearity, all we're referring to is that if you zoom in enough, you will see something that is very linear. What condition must be satisfied? Well, it must be differentiable. Now, that's the big thing, is we got to have differentiability here. And there's all those differentiability things we talked about. You can't have like a cusp like that and think that you're going to get local linearity, or you can't have like an asymptote and think that you're going to get local linearity at that point. Of course not. It's got to be differentiable. So the tangent line can be used as an approximation of the curve near the point of tangency, since the y values are almost the same. How close? Well, it actually depends on the situation. It'll depend on the situation how close you got to get and how long this is a good estimate. And by the end of the lesson, I think I'll be able to show you how you'll sort of know when you've got a good estimate or not. So we know that the equation of a line can be written in point slope form. So instead of using y equals mx plus b, it's going to be more convenient to use slope point, which is y equals mx minus p plus q. And if that has slipped into the recesses of your mind. All we're doing is, this is the equation of a line with slope m through a point PQ. Okay, and that's going to be a convenient form to use. Now, if we look at the picture, and we on the picture there, we've got a curve with a tangent on there, and if we look at that, the point of tangency is A, comma f at A, and all we're saying there is to get that point, we take any A value you want, sub that A value into the function, and you'll get the Y value that goes with it. And at that point, the slope of the tangent is f prime at A. So I've got a point and a slope. I'm trying to tie these two things together. I've got a slope point equation, and I've got a point and a slope from my picture here with tangents. And so what I get is y equals, and I'm just using this, this is where I'm looking. Let's be clear about where my eyes are looking as I'm doing this. I'm looking here. I'm going, okay, this is the equation I want to use for the equation of a line. And so the line will have this equation. It has slope m, but from below, instead of using m, I'm going to use the slope, which is f prime at A. And then I've got to go x minus p, but it's x minus, I've got a point right there. There it is right there, A comma f at A. So it's going to be x minus A for the x value, and then plus the y value, f at A. See? Let me just get a little red color here going here and go, all I did is take this slope and put it in there as the slope. And then I took, it's kind of the color here, I got a green going here. And I took this point and put it in there and there as the point. And then so you get the formal linearization, it's called, is that you find the linear approximation to the function. That is, we're approximating the function by this line here. And all they do is switch the order here. They just move this one over here and move that one over there. They switch the order and they, okay, if f is differentiable at A, then the equation of the tangent line, L at x equals f at A plus f prime A x minus A, just wrote in the different order. It's called the linearization. And it's an approximation of the curve, and sometimes we call it the standard linear approximation, and the point A will be at the center of that approximation. Now here I go, and let's just see how the zooming works on Microsoft Word here today. And if I zoom in, you'll see on that picture that if you look really close, and let's just make a little circle on there, and I'll make actually a little highlight on there. See right in that area there, do you see how the blue and the red are really close to each other? So it's a great approximation when we're close to A. And yes, if we get too far from A, it's not going to be a good approximation anymore. How close is close enough? Let's just leave that discussion on the shelf a little bit. Let's just experiment with this thing a little bit, and we'll get used to very quickly what a good approximation means and how close we have to stay. For now, we can say if we're close enough, and that's the nice thing about this word neighborhood. And when we say neighborhood, we say, okay, locally, or in a close enough domain, in a close enough set of x values, it'll work out good. Well, okay, that's enough. That's enough about the theory. Let's actually get to one, and I'll be able to use Desmos to show a little bit more about what's going on. So it says determine the linearization of f at x equals square root of 1 plus x at x equals 0. So let me just write down that linearization again. To do the linearization, I go f at A plus f prime at A times x minus A. There we go. Now, in this case, they've given me the A value to use. They've said we want to work around an x value of 0. That's going to be our center value here. That's if you look in the picture there, that's the x value we're going to use as our center. So here, my linearization actually is find the function value at 0, then find the derivative at 0, and x minus 0. Now, I left the x minus 0 in there. Of course, you don't have to do that. You can just have the x in. Okay, so there's two things I got to figure out to do this linearization. I need f at 0. That's easy enough. I just sub that in, square root 1 plus 0. 1 plus 0 is 1. Square root of that is 1. So I get f at 0 is 1. Then I need f prime at 0. Well, I'm going to have to first do a little bit derivative stuff here. F at x is 1 plus x all to the 1/2. So f prime at x, 1/2, 1 plus x to the negative 1/2. And we'll just simplify that up a little bit. F prime at x equals 1 over 2 root 1 plus x. And it only takes me a second after that to get f prime at 0. That's what I really wanted. It's 1 over 2. And then square root of 1 plus 0. Let's see, in the square root I get a 1. So square root of 1 is just 1. I just get a 1/2 here. So there's the calculation part of it. I'm ready now to do my linearization. L at x equals f at 0, which was 1, plus f prime at 0, which is 1/2. And I don't need that x minus 0 anymore. I can just write that as x. Now, before you leave, before you let your brain explode and go, what the heck is going on here? Okay, let me just show you in Desmos these two things that I've accomplished so you can see what we're talking about here. I just got to fix my zoom here. Nice thing about Desmos, a nice free app that you can use here. And let me just say, okay, so the original function was y equals square root of 1 plus x. There's the function they want me to do the linearization at. And my calculation said that the linearization of this would be y equals, oh, big moment coming up. So if you're like, I don't even know where these values are coming from, how are you coming up with this? This little demo here I'm doing here in Desmos will really show where all this is coming from. So 1 plus 1 over 2 x. That was the linearization I found. And so here it is, the big reveal. What we are saying is that close to 0, that was the x value, sorry, the a value that they wanted us to use. Well, it was also the x value, but close to 0, this red graph, square root of 1 plus x, can be estimated by the blue graph, 1 plus 1/2 x. And I love the zoom that I've fallen into here because you can really see, like as you go way off on the right-hand side of the screen, the blue graph is not a good estimate to the red graph. And if you go on the left side of the graph there, you see that the blue graph's not a good estimate of the red graph. But if I just zoom in a little bit, it doesn't take much zoom before you go, oh, well, I guess in there, it's a pretty good estimate between, I don't know, it looks like negative 0.2 up to positive 0.2, something like that, that the blue graph is an excellent estimate of it. You're like, okay, that's fine. I see what you're saying is it's a good estimate, but where are you getting these values from? Well, it's actually really, really good where the values come from. The two values that we had to work from are, we wanted the initial value at 0, f at 0, which was 1. We need to know, okay, that's fine. We want to estimate around 0. We need to start at whatever the function value is at 0. It better be perfect at the x value of 0, and it is. So you sub it in, you say, what's the perfect value to start at? 1. 1 was the perfect value to start at. Then you say, okay, and then what's the slope at that moment? We better have the exact right slope right there at y equals 1, at x equals 0. At that moment, we better have the right slope. So let's just find the slope at x equals 0. And so you find that slope and you say, okay, well, the perfect line would have y value 1 and would have the slope of this graph. And that's where all that stuff comes from. So the development that happened on that previous page for linearization was all very fancy. But in the end, all we were doing was saying, find the y value that matches right up for the linearization, and then find the slope that matches right up at that x value. And so that's where this f at a and f prime at a come from. You say, find the right y value and the right slope. And then you can have your x minus a after that and say, okay, well, I don't know how good this estimate's going to be, but well, hey, here we're going to test it out. Let's test it out. It says, find out, use your linearization to find the value of square root of 1.02. By the way, I need to mention that finding square roots in any kind of way without punching in your calculator is a very, very difficult idea. And for many, many centuries, doing square roots was no simple task. But things like this made it so that you could estimate square roots very, very nicely. And you're gonna see how that's done. We're gonna say, no, to find this square root, we're gonna go L at x equals 1 plus 1/2 x. And what are we doing? We want 1.02. So our x here is 0.02. Okay, an important little distinction there is that inside the brackets was 1 plus x. So the actual x value I need to find the square root of 1.02, the x I need is 0.02. I want to be 0.02 away from and the a 1 underneath the brackets here. So I go 1 plus 1/2 of 0.02. I don't even need a calculator to think this out. I can go half of 0.02 in my head and get 1.01. So my linearization tells me that a good estimate of square root of 1 plus 0.02, a good estimate's 1.01. Well, just to know what's going on, let's get their calculator out and better check what kind of number we get here. And so I put it in my calculator. I go square root 1.02, and I check it out, and I punch it in and get the decimal, and I get square root of 1.02. Oh, see, it equals 1.00995. I got 1.01, and wow, that's really close. Now, it brings up another little point here, is that we really should be going, instead of equals, we should have these little squigglies to say, well, it's approximately 1.01. But boy, what a great approximation. We were close enough to 0 that our approximation was excellent here. And I think if you actually do your little scientific percentage error thing, you're going to get like an error of less than 0.005% or something like that. It's really quite accurate. Oh, and so I did that there. Use the calculator to determine the accuracy. I did that right there. Now, we can extend these results to any power of 1 plus x. Specifically, for small values of x, close to 0, we get 1 plus x to the k is always going to be 1 plus kx. Does that hold here? Right here. When this was power 1/2 here, so this was 1 plus x to the 1/2, it came out to 1 plus 1/2 x, very simply. And it's pretty easy to extend that out. And I might not be able to resist in a minute really proving that. But let's just use it for now, see how it's used, and then I'll do the proof in just a second. So, weirdly, when they write it like that, that can be a confusing version of it. So when they give you a formula with x's in it and then immediately try to get you to use it with x's, it can get a little confusing how things go. So I'm just going to rewrite this with y's instead. I'm going to go, well, that means that 1 plus y to the k can be approximated by 1 plus ky. And then when they go to use x's, I don't have to be confused. So they want third root of 1 minus x, and they want the linearization of that. So I'm just going to write that in the form we want, which is 1 plus negative x to the 1/3. And that writes it in the form that I want to do this linearization. I say, okay, well, 1 plus something. See, my formula says 1 plus something. And what's the 1 plus something? Why, the 1 plus something is 1 plus negative x there. So then when I go to do this, what I get is the linearization is 1 plus k, and my k here is 1/3, but then my y is actually a negative x, and so I get a nice linearization of 1 minus 1/3 x. So it changes sign on you there. Just a nice useful formula for finding linearization. So let me just write linearization there. And change those to little squiggles. Sometimes you don't see people use the little squiggles because we know what we're talking about here, but technically we should have little squiggles here. Let's try another one just to really get the feel for that again. In this case, I got a little carried away with my linearizations there. That's equal, and that was the linearization. Okay. So this is equal to 1 plus negative x to the negative 1. You see my formula up there for linearization asks for 1 plus something. So I make it into 1 plus negative x. And so now I can use that as my y value and use that formula up there. And the k value is negative 1. So the linearization is 1 plus the k value, which is negative 1, times the y value, which is negative 1. So those two negatives nicely cancel. How sort of cool is that that's the way it all plays out? And so then what I get here is a linearization that's all the way back to, sorry, that's an x there, 1 plus x. Last one of these type of deals is this one is now 1 plus 5x to the fourth. So I can write that as 1 plus, the plus is right, but this crazy 5x to the fourth in there, and then we're back to an exponent of 1/2. So my linearization here, and maybe I'll make some notes here, I'm going to get k equal to 1/2 this time, and I'm going to get y equal to 5x to the fourth this time. So my linearization, I hope I have enough room here, is 1 plus the k value, 1/2, times the y, which is the 5x to the fourth. And so I get a linearization here of 1 plus 5/2 x to the fourth. That nicely dealt with the 5/2 x to the fourth without having to do anything too crazy there. So that's a nice result. You know what? I'm not suggesting you have to memorize that result. It's just it's a nice result to work with when you're doing linearizations, is that it doesn't always have to be some crazy development every single time. You're like, okay, fine, that's a nice trick. Can we get back to just regular linearizations to see how that works again? And then let's go after this one here, because it's a little more how do we use it type of thing. Okay, this says use the linearization to approximate the value of square root 123. And nothing we've used so far no linearization we've done so far can be used to do square root 123, because 123 is not close to 0. Yeah, so that is not going to work at all. So what we need to do is think of another way to handle this and find a value close to 123 that we could approximate from. That is something we can take the square root of that's close to 123, and then we could do the linearization off of that. And so the number that is close to 123 that I can take the square root of is square root 121. And, maybe I got to trial and error that a little bit and go, well, it's 10's pretty good. 12's 144. That's not great. Oh, 11. 11's really close. So what I'm going to do here is I'm going to use an f at x equal to square root of x, but I'm going to use an a value of 121, and then I'm going to work a linearization around that 121 so that I can do this estimate. So f at x equals root 121. So my linearization that I'm going to use is, let me just write it down here before I do my calculations. Linearization of this function, root x at a value of 121 equals approximately f at a plus f prime at a times x minus a. Well, okay, I've got the a. So linearization of x, I'm going to use f at 121 plus f prime at 121 times x minus 121. This will be the approximation of the square root of something that's close to 121. This will give a nice approximation of that. So the two things I need is f at 121 and f prime at 121. So I can do f at 121 up here. F at 121 is square root 121, so that's 11. Now, for f prime, I'm going to need f prime at x, and that's 1/2 x to the negative 1/2, or it's 1 over 2 root x. That's f prime. But I want f prime at 121. What's the slope there at 121? And so I get 1 over 2 root 121, and I get 1 over 22. So the derivative there is 1 over 22. So if I want to estimate the value of the square root function close to values of 121, then I need the value at 121, which is 11, plus the slope at 121, which is 1 over 22, and then I got to go x minus 121 to be close to that. There's the linearization of this thing. And then I want a specific value. I want linearization at 123, and so I need 11 plus 1 over 22, 123 minus 121, and I get 11 plus 2 over 22, and I actually get a nice fraction here, 11 and 1/11, but let's get it down to a decimal. Punch that in your calculator, and you get 11.09 repeated. And the question is, how good an estimate do I do? Now, you know what? In big picture, I want to establish that that was a pretty easy calculation. If I told you before this even started to do square root 123 in your head, well, you might be good enough to go, well, it's 11 point something, but that's probably the best you could do is a little guess after that. Now, with a little bit of algebra, I can get a really good estimate to the square root of 123. And you're like, well, that's nice, but I got a calculator to do square roots. Just hang on for another couple of lessons and another chapter, and you're going to see the incredible things we can do with what we're building here. So for now, it's a cute little way to find square roots. If that's all you think about it, I guess that's okay for now. But as things develop, you're going to see there's more to this than meets the eye. But anyways, in the meantime, we better actually check to see how good an estimate this was. Find the square root of 123 using our calculator, see how good we did. And incidentally, we don't need our calculator. Once we get enough math available, we can find out how good an estimate this was without using our calculator to check it. That seems sort of redundant, but we just need a little more experience in all this. So I get 11.0905 and 8. So, this is, there's more decimal places there, but so pretty good. It's only different by 4/10,000ths. So we'll really take that as a really good estimate here. So that shows you the kind of thing you want to do with linearization. When you got a function that's too hard to evaluate without a calculator, do a linearization of it, close to it, and then you'll come up with a nice function that you can sub into and use quite easily. And like I say, differentials, if we get time in the last couple of days of the course, we'll take our run at differentials, but we don't really need that right now, even though it's a fun, wonderful topic, but we'll have to get to it a little later as we stay focused on the stuff that's important in this chapter. Have a great day.